Hi, I'm Zor. Welcome to New Zor Education. I'd like to start a new topic. It's related to trigonometric inequalities. Well, first of all, which inequality can be called trigonometric? Well, obviously, the ones which involve some trigonometric function. That's no big deal. Now, let me just spend a few minutes talking about general approach to how to solve inequalities. So let's say you have some function and you would like to solve inequality of this type. Now we are talking about real function, real arguments, and real constant a. How this particular inequality in general can be approached to solve? Well, we will deal with smooth functions, continuous functions. So if I will have the points which are solution to this particular equality, let's say points are x1, x2, etc., xn. So there are n solutions to this particular equation. Then look at the graph. If this is a function f of x, and this is a, and I found these points where function f of x is equal to a. x1, x2, x3. So it's obvious that for a smoothly behaving function that we are considering only these smooth functions. If I have, let's say, these 2 points, then the function in between these points should be either less or greater than this particular level, right? So if at x2 it's equal to a and x3 is equal to a, and there is no points in between where it's equal to a. So these are 2 consecutive points where f of x is equal to a. Then in between it's either less or greater than 0. So to find out where exactly these particular conditions are held, we have to find the points where the corresponding equation becomes an identity, and then examine all the intervals in between these points. Less than x1 in this particular case, between x1 and x2, between x2 and x3, and greater than x3 in this particular example. So this is an approach which we will take to solve trigonometric equations as well. So if we have a trigonometric equation, we will try to solve the corresponding if we have an inequality, then we will solve the corresponding equation, and then we'll examine the intervals in between the solutions of this equation. It might be a little bit complicated by the fact that trigonometric functions are periodic, which means the same solutions to the same equations actually are numerous, countable number of times on each period. But that's not a big problem. We will just solve the equation on some interval which is the basic interval of periodicity, and then we will just add the period to all the solutions which we will get within this particular interval. Okay, so that's some kind of introduction to this particular lecture. Now let's go to particular examples. And so my purpose during this lecture to explain solutions of inequalities like tangent of x less than equal to a, cotangent, sine, and cosine, basically, four cases. That's number one. Number two, I will usually use less or equal, but it's trivially expandable to less or greater or equal or any other things. The difference is whether I will or will not include the points exactly where the tangent or sine or cosine equals to A. All right, so I will start with tangent, and the reason is exactly the same as my starting with tangent for equation, because interval of periodicity of tangent is the same as equal of monotonic behavior and existence of the inverse function arctangent, right? So if this is your tangent minus pi over 2, pi over 2. And the pi is a period. And this is exactly the interval where function tangent behaves monotonically. It's monotonically increasing. So I will solve the equation, inequality on this period from minus pi over 2 to pi over 2, and then just add pi, which is pi is a period, right? And in this case, it's very simple actually, because wherever the A is positive or negative, let's say it's negative, for instance. This is A. So this point is dividing the whole interval of periodicity into two parts. On the left, I have below A, and on the right, from this point, this is the point. And to the right of this point, to the end of the period, I have greater than A. So solutions to this particular inequality are very simple. Let's call, well, this particular point, what is this point? This is solution to equation which is arctangent A, right? So this is the point on the x-axis where tangent is equal to A. So what I can say about solutions to this particular inequality is that x should be, we need greater or we need less than or equal. So it's greater than minus pi over 2. It's not equal to pi over, minus pi over 2 because it's undefined. And less than or equal to arctangent of A. So this is an interval from this to this, where the function tangent is below or on the level of A. Now, the general solution obviously is like this. I add pi times n, where n is any integer number, to here and to here. And this is a countable number of intervals. This interval, then this interval, and this. Countable number of intervals, and each interval is a solution. So the union of all these intervals is the solution. Well, that's it. It's simple with tangent, right? Now, let's go to cotangent. That's where it's as simple, actually. The period of cotangent is also pi, but it's better for me to examine the function cotangent on the interval from 0 to pi. It's also interval of periodicity. I mean, any interval which has the length of pi is a period of, it is an interval of periodicity. But why did I choose this particular one? Well, because cotangent behaves monotonically. This is p over 2, pi over 2. Right? Now, on this particular interval from 0 to pi, cotangent behaves monotonically. So, my inequality, now this is, let's now use the positive A. So this point is arc cotangent of A. One and only point where the equation has the solution. This is the solution. So on the left from this point, my function cotangent is above a, and on the right it's below a. So if I need the solution to this particular inequality, I have to do it the following way. I have to, we need less than or equal. So from this, x less than pi. From this to this, not including the boundary. So the endpoint is not included here, but it is included in this case because there is an equal is acceptable solution. All I have to do right now is, as before, add pi n to both sides. That's the general solution. It's exactly the same as in case of a tangent. It's a small interval within the period, and then I expand it to all the periods. And what's the kind of simplicity in case of tangent and cotangent? Because the interval of periodicity, which in both cases is pi, is the same as an interval of monotonic behavior and existence of the inverse trigonometric function for any real value a. So no matter which a I choose, I can always find this particular solution to this particular equation. So there are no restrictions basically on a or anything else. And it's easy to deal with monotonic behavior. It's just one inequality. Okay, situation with sine and cosine is slightly more complex, and let me explain you why. Let's approach again this graphically. Now, in case of, well, let's say with sine. So I will consider sine on a minus pi to pi. Not exactly symmetrical, something like this. Minus pi to pi, okay? This is sine. And we are looking for solutions to this particular inequality. Well, first of all, it's obvious that if a is 1 or above, then every x would be actually the solution, because sine cannot be greater than 1. So let me just do it. Case number 1. If a is greater or equal to 1, then x can be any real number. Now, second case. If a is less than minus 1, if it's below this level, less than minus 1, then no solutions. Because any x would be greater, and we need less than or equal. And only if a is in between these two boundaries, from minus 1 to 1, we can talk about some meaningful solutions, non-trivial solutions. I mean, everything is meaningful, but non-trivial solutions. All right, so let's examine a couple of cases separately. And here is why. If a is less than 0, negative, the solution to this is one particular interval here, right? Only these are solutions. Now, if a is here, then I have actually two different areas within the period where my sine is less than a. It's this interval and this interval. The whole this period, the whole this interval, because from this to this, sine is below this line and above this. So let me do the third case and split it in two halves. if a is greater than 0, so a is above, I have two different intervals, right? Now this point is obviously arc sine of a. So my solution is from minus pi less than or equal to x to arc sine of a. That's one particular interval, right? And the second interval is, now this is exactly in length, this particular interval is equal to this one. So it's pi minus, so it's pi minus arc sine. So from pi minus arc sine of a, x, and 2 pi. These are two intervals we're talking about. And obviously I have to add 2 pi n, because in case of a sine, the period is 2 pi, right? I have to add it here, and here, and here, and here. So for a greater than 0, this is the solutions. Now, and for, yes, what I mean is a is still less or equal to 1. It's not just greater, because these cases I have to, so it's from 0 to a to 1. And this is from minus 1, yeah, you can put equals here, to 0. Now, what happens in this case? So, it's this case, when a is below 0, so I have only one interval. Now, what is this point? This point is arc sine, right? Because the interval of periodicity is from minus pi over 2 to pi over 2. This is interval of periodicity. And for a, this is arc sine. And it's negative, by the way. So, how can I get to this point? Well, that's minus pi minus arc sine of a, right? I have to move to the right. Now, arc sine is negative, so I have to subtract to move to the right. 2 arc sine. So that's the solution. All right? From minus pi minus arc sine, that gives me this point, and this is arc sine, this is this point. And again, I have to add 2 pi n in both cases. Okay, that seems to be it. Now let's go to cosine. Now, the graph of the cosine is like this. It's symmetrical, also from minus pi to pi. This is pi over 2, and this is minus pi over 2. And the situation is basically very similar. That it all depends on the value of a. If a is greater than 1, again, actually even equal as well, then x can be any real number. Second, if a is less than -1, no solutions. Now, the third case, if a is in between -1 and 1. So this is -1 and this is 1. So if a is somewhere here. But you see, because cosine is a symmetrical function, no matter where I put this line, a here, and in this case I have this interval and this interval where the function cosine is below a. Now if a is negative, I still have the same two intervals here, one interval where it's below a and another. So it's always two intervals. In the case of a sine, sometimes I have one interval, sometimes two. In this case, in case of a cosine, I always have two intervals. So what is the interval of periodicity I took? The minus pi to pi. What's the interval of monotonic behavior for a cosine? Well, we usually, traditionally, to have arc cosine, we take it from 0 to pi. So that's where we should really look for a cosine, for arc cosine. This is arc cosine. Now in this case, this is arc cosine. So arc cosine is always from 0 to pi. Okay? Now, how can I identify the left point? It's always minus pi. So it's always minus pi. And the right point is minus arc cosine. Right? If this is arc cosine or this is arc cosine, then this is minus arc cosine. Minus arc cosine of A. So that's one interval. And the second interval is from arc cosine to pi. From arc cosine of A to pi. So these are two intervals which are describing all the values of x on this particular period from minus pi to pi, where the cosine is less than or equal to a. And again, as usual, I have to add 2 pi m. So that's the solution. So what we have done, we have, number one, analyzed just a general approach how to solve inequality using the corresponding equation. So instead of finding where it's less or greater or whatever, we will find where it's equal, and then all the points in between the equality are inequality. And we are definitely using the smoothness of the graph of the function. Now, then we have analyzed the behavior of functions tangent, cotangent, sine, and cosine, and investigated how to find what exactly are the values where these functions are less than or equal to some value. And as I said before, to transfer it to another inequality like greater or equal or strictly less, it's trivial, so I'm not going to spend time on this. What's interesting is, again, that tangent and cotangent are a little bit more convenient in terms of their interval of periodicity is exactly the same as interval of monotonic behavior, so there is only one point where the corresponding equation has a solution. So it's always from some edge of the interval of periodicity to this point, or from this point to another edge of periodicity, and then you add the period. With the sine and cosine, it's slightly more difficult because there are one or two intervals within the period, and it's all related to the fact that interval of periodicity is not the same as interval of monotonic behavior for both sine and cosine. That's why they had to consider different cases. Well, that's it. I do recommend you actually to repeat again these little calculations which I did. And what's most importantly is you have to solve the problems, and I will definitely have some problems following this particular lecture, which explains just general theory. There are numerous examples of how to apply this knowledge and how to train your mind to find specific ways to resolve this or that particular inequality. These are simple, elementary ones. These are the end road. When you are given a particular inequality to solve, this is the very end. So whenever you will reduce your original inequality to this, then you basically understand how to do it. But to reduce it to this particular form, that would require some ingenuity, and that's why the problems are all about. And well, that's why actually the whole course is about, to develop your creativity and ingenuity. Well, don't forget, everything is on unizor.com. It's a free site, and you are encouraged to register, because that would enable your supervisor or a parent, maybe, or yourself, if you want to play this role, to enroll you in a particular topic, which will further enable you to take exams. Exams are important because there is no explanation, like I'm doing right now, what's the solution. It's just an exam, and you can take it as many times as you want, but that would really kind of check the level of knowledge and expertise which you have developed. Thanks very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. Well, it's time to solve a few trigonometric inequalities. I did have some introductory lecture about basic trigonometric inequalities, like sine of x less than a. So now let's just solve some problems using certain methodology which might really be very helpful. So I have 3 problems. They're not really difficult, but there are certain calculations which I hope I will not get lost in. Okay, the problem number 1. Tangent of x plus cotangent of x less than or equal to a. Alright, so the first complication which strikes our eye is that it's not just simple tangent less than something. It's sum of 2 different trigonometric equations. Some of them each part we can actually solve. Tangent is less than something, and cotangent is less than something. That's okay. How about their sum? And what kind of a function is the sum of tangent and cotangent? Just to better understand what this is all about, I prefer to draw a graph. So let me just think about the graph of this particular function. So this is, let's say, from minus pi over 2 to pi over 2. I know the tangent is monotonic, and it looks like this. That's our tangent. Now the cotangent is monotonic on 0 to pi, right? So it's like this, and it's decreasing. And similarly, here we will have minus pi, so it's this, right? Now, I would like to have some common period of periodicity, interval of periodicity, so I will choose from minus pi over 2 to pi over 2. So let me just wipe this out so it does not disturb us, and this. And let's sum them together. Now, obviously, the minus pi over 2 and 0 and pi over 2 are asymptotes, because in this point tangent is going to infinity. At this point cotangent goes to some infinity, whatever it is, and at this point, again, tangent is equal to infinity. So these are asymptotes, minus pi over 2, 0, and pi over 2. Now, at this point, they're both of them the same. And what happens then? Then one function goes to infinity and another goes to 0. So basically we are adding something to this, and it will go to this way. And on this side, from this point, it will be exactly the same, but it's the tangent which will go to infinity, so the function goes this. So my total graph would look like this in this case. This is my sum. Now similarly, on the left from the 0, this both are negative, so the sum will be like this, and then it goes to negative infinity. So my graph would be like this. Okay? Now, these are points. They are right in the middle, by the way, between 0 and pi over 2. It's pi over 4, actually, which is 45 degrees, and tangent and cotangent are equal to 1. So their sum is equal to 2. So this looks like this is a 2, and this is minus 2 correspondingly. But this will make sure, actually, that this is really true. But in any case, I wanted to have a feeling of what actually the graph of this function represents. Now, if I would like to have less than or equal to a, well, it depends. If a is between these two, then the bottom part will be completely inside this interval. If it will be below 2, I will have two different intervals, left and right, and it will be above 2, below minus 2. But if it will be above plus 2, I will have the whole branch of these guys and piece of this plus piece of that on the other side of the intersection. So it all depends on where y is equal to a straight line intersects this graph. So in this case, like I just draw, it's greater than 2. Now, all this part would be part of this solution, well, except 0, of course, where it's not defined. And on the right, from the right part, it will be on this side. Again, not including the pi over 2. So that's basically my general approach to solving this particular inequality. Now let's do it analytically. Now, again, we have the problem, tangent and cotangent, and we don't like it. However, we do know that cotangent is 1 over tangent, right? So what I have here is tangent of x plus 1 over tangent of x less than or equal to a. Now, that's a little bit easier, but not that easy yet. Now, obviously, I have to exclude from all the solutions where the tangent is undefined or the tangent is equal to 0 because the cotangent is undefined. So basically it goes to x not equal to 0, pi over 2, pi minus pi over 2, etc. So basically we can say that it's pi over 2 times n, where n is any integer number. So these are prohibited values, and we should really exclude them from all the solutions. Now, after this is excluded, I can multiply by tangent of x, because it's not equal to 0 now, since we excluded these values. And what I will have? I will have tangent square x plus 1 less than a tangent of x, right? Or tangent square of x minus a tangent of x plus 1 less than or equal to 0. Now, let's call tangent of x by some letter v, some variable. Now, this is, in terms of v, this is a quadratic equation. Quadratic inequality, sorry, right? And we know how to solve this quadratic inequality. Because graphically speaking, any quadratic inequality can be represented as what? As a parabola. In this case, it's this way. So depending on where exactly are solutions to the corresponding equality, where the whole left part is equal to 0, solution to this are all these values of argument in between these 2 points, right? Because that's where the whole parabola goes beyond, below 0. So let's solve this equation. We will find what v's are representing the solutions to the corresponding equation. So if I have equations equal to 0, v squared minus ab plus 1 is equal to 0, then solutions are 2a plus minus square root a squared minus 4, right? That's what the first and second are. That's the solutions. And our condition when it's less than or equal to 0, it actually means from that with a minus to that with a plus. So in between these 2 values, my quadratic polynomial is less than 0, right? So we have solved the corresponding equation, find solutions, and in between these 2, since the coefficient at v squared is 1, so the parabola goes upwards, and in between these 2 solutions, it's below the 0 level. So what we have actually reduced our original inequality is that tangent of x should be greater than this particular expression, but less than this particular expression. So we have reduced one particular trigonometric inequality, reduced to a combination of 2, to the union of these 2 conditions. Correct? Well, that's easy, because we know what to do in this case, because we can solve each one of them and then take the union. What I would like to add, it's very clearly visible here that a should be at least 2 by modulus. It should be either greater than 2 or less than minus 2, because otherwise my expression under the square root would be negative and there would be no solutions. So solutions exist only if a is greater than 2 or less than minus 2, which basically corresponds to whatever I was just talking about, right? Okay, now, how to solve these guys? Okay. Well, if I would like to solve this one, the left part, so tangent is greater than some value. Now, the tangent is this, so if some value is wherever it is, so it's greater than, so it should be greater than arctangent, right? So solution to the left part is x is greater or equal than arctangent of this guy, right? This is minus. That's solution to this one. Now, solution to this one is x is less than or equal to arc tangent of a plus minus 4 divided by 2. Now, and obviously in both cases we should not really go beyond our interval where we are looking for solutions. So if x is greater than this one, then that should be less than or equal to pi over 2, and in this case it should be greater or minus pi over 2, right? So whenever a is greater than 2 by absolute value, we basically have this particular type of equations, of inequalities, which we have to combine together into some kind of a solution, right? All right, so what we can say is the following. If a is somewhere here, then above 2, then we can say the following. These 2 points represent arctangent of a minus square root of a squared minus 4. Let's call it P and Q. This is P and Q. So this is, it's not really P, it's arctangent of P and arctangent of Q, right? So in this particular case, so what we have is, our solutions are all of these guys, all the negative except minus pi over 2 and and except 0, because that's where it's not defined. And then from 0 to arctangent of this particular expression of P. So let's call it P. Let's call it. So we will have from minus pi over 2 x to 0, except we don't have equals, obviously. And then we have from 0 to including arctangent of this expression, which I call P, but anyway, it's a minus square root of a squared minus 4 over 2. And in addition to that, we have another interval from arctangent of a plus square root of a squared minus 4 over 2. To pi over 2. So that's what we have, right? Completely this thing, that's this. Then this piece, oh, no. It's not before that, it's in between these things. So I'm wrong. So we have to combine these two together. So it's not to the left and to the right, it's in between actually. So it should be from minus x to plus arctangent of a plus square root of a squared minus 4 over 2. So we have to combine these two together, right? So that's what we have. So this is exactly the same as whatever I put here, except I applied these particular restrictions. No pi over 2 and no 0. That's why we did this. Now, if it's less than minus 2, I will have correspondingly from minus pi over 2. So this is for a is greater than or equal to 2. Now, if I have a is less than or equal to minus 2, I will have two pieces from here. The one from minus pi over 2 to arctangent, so minus pi over 2x to including arctangent of this thing, and this piece from the intersection to 0 from arctangent of a plus square root of a squared minus 4 over 2x, not including 0. Right? Not sure which is plus and which is minus. Let's just think about it. If a is negative, then this is more negative, right? Than this. So that's correct, right? So it's two intervals here. Now, what if a is in between? Then the whole solution actually is not working because this square root cannot be extracted. But if a is in between, all you can say is that for minus 2a plus 2, you have x from minus pi over 2 to 0. So all this part, if a is in between these two values, then it doesn't really intersect the graphs, which means everything which below is this whole piece. So that's what we have as a solution. So these three cases. Now, how to get the complete solution? Add pi n to each one of those, basically, because we have to add the period. So this is a complete solution. Depending on a, we have come up with different formulas, different intervals, and then we added the period. But the principle is basically the same. If I would like to find out where some expression is, let's say, less or equal to a, I try to graph this expression, more or less, approximately, I'm not saying it's exact, and then intersect it with y equals to a, and see on which side values are located in this case. Okay, let's move on. Well, as you see, it's not really very difficult, but it's involved. There are certain calculations, and you have to consider certain cases. It requires certain accuracy, and I'm not sure I'm perfect in this, but anyway, trying. Okay, now, next one. 6 cosine square x plus 5 sine x less than or equal to 7. Again, the problem is we have a mixture of different trigonometric functions. However, it's obvious that cosine square can be converted into sine square, and then you will get a situation which is relatively similar to whatever was in the previous problem. We have a quadratic inequality, so it's 6 minus 6 sine square of x plus 5 sine of x less than equals to 7. So it's a quadratic inequality which we know how to solve. We will call sine of x v, and what I will have is, it would be minus 6 v squared plus 5v minus 1, because this is 7, this is 6, less than or equal to 0. Or I like to have plus at the square, so I will have 6v squared minus 5v plus 1 greater than equal to 0, right? I reverse the sign of the left part and reverse the equation to the opposite one. Now, what is this? This is a parabola, right? Directed upwards. So all we need to know are two values where it intersects the x-axis. So it's basically the solutions to the equation, to this equation. All right, so what are the solutions? 12, 5 plus minus square root 25 minus 4 times 24. So this is 5 plus minus 1 over 12. So I have, if it's minus, it's 4, so it's 1/3. And 1/2. 1/2 and 1/3. Two solutions. So, how can I use this? Well, basically, if I'm looking for something of this particular polynomial to be greater than 0, it's quadratic polynomial, it's parabola. Greater means it's left from the left solution and to the right from the right solution, right? Again, parabola. So it would be to the left and to the right of this. So that's the that's where my parabola is positive. So what it goes to is the following. It's sine of x is less or equal than the smallest one. That's one group of solutions. And sine of x is greater or equal than 1/2. That's another group of solutions. Right? Now let's go to the graphic. Now it's easier. So, from minus pi to pi, sine goes like this. Right? This is minus 1, this is 1, and we're interested in 1/2 and 1/3. So one group of solution is less than 1/3. Now this is 1/3, this is 1/2. So less than 1/3 is everything from minus pi to this point and from this point to pi, right? So from minus pi to this point. This is obviously arc sine of 1/3. That's one interval. And the second interval greater than this particular point. Now this particular point is pi minus arc sine of 1/3 and ends at pi. By the way, I specify the interval as two numbers, the left and the right part, and the square bracket means it's including the endpoints. If it's not including, like in case of tangent, I use the round parentheses. Now, what about 1/2? That's yet another solution. So here we have greater than, so it means it's in between these two things, from here to here. So this is obviously arc sine of 1/2, and this one is pi minus arc sine of 1/2. So these three intervals within, so it's this one, and then the middle one, and the small one. These three intervals represent the solution on the interval of periodicity from minus pi to pi. So to get the complete solution, you have to add 2 pi n to each one of them. Both ends, obviously. Well, that's it. By the way, in this case, as in the previous case, what I did, I have reduced my original inequality, which involved different trigonometric functions, to a quadratic inequality in terms of one particular trigonometric function. In case the first one was tangent, the second one was sine, but in both cases I have obtained, from analyzing the quadratic inequality, I have obtained the condition, a very simple condition in this case, on the original trigonometric function, on tangent or sine. And then that I have converted into the interval for x, which was supposed to be. Next one. It's kind of similar, by the way, so far. This will also be similar. Okay. Now, as usual, I don't remember the formula for sine of 3x, but I do remember it's something like some number multiplied by sine x and some number multiplied by sine of 3x. So I'm going to obtain this formula right now. But why am I talking about this? Well, because if this is a combination of sine and sine cube of x multiplied by sine, it will be sine square and sine to the 4th degree, which brings me to the point that it would be almost a quadratic equation, but instead of having just an independent variable, I will have sine square as a intermediate variable. So let's see. First of all, I don't remember, as I said, sine of 3x. Let me just derive it. So it's sine of x plus 2x, right? So it's sine of x times cosine of 2x, which is cosine square x minus sine square x, plus cosine of x times sine of 2x, which is 2 sine x cosine x. And cosine square I will also convert into 1 minus sine square. 1 minus sine square x. So I have here 1 minus 2 sine square. So if I multiply by sine, it will be sine x minus 2 sine cube x plus 2 sine x times cosine square, which is 1 minus sine square, equals sine square, sine x and 2 sine x would be 3 sine x minus 2 sine cube and minus 2 sine cube. So it's minus 4 sine cube. That's what it is. Okay, so I will use it here. I will use this. This is completely invariant transformation. So I will have sine x times this, which is this, which would be 3 sine square x minus 4 sine to the 4x less than minus 7/16 by quadratic equation, right? So what I'm doing here right now is quite obvious. I will put sine square equals to v. And what do I have? I have minus 4v squared plus 3v, let's put it here, plus 7/16 less than or equal to 0, right? That's my equation. Well, again, I prefer to have the positive coefficient at v squared, so I will have plus 4v squared minus 3v minus 7/16 greater than equal to 0. So I reverse the sign here, and I reverse the sign of inequality. Okay. First, what we have to do, how to determine the points where this particular parabola is greater than 0. It's left to the left solution when it's equal to 0, and to the right from the right solution, right? So we need two solutions of the corresponding equation. So it's 8. This is 3 plus minus square root of 9 minus, so it's plus because it's minus. 4 times this, 4 times 4 is 16, this is 16, so it's just 7, right? 9 plus 7 is 16, square root is 4, so that's what I have. Which is minus 1/8 and 7/8. And this is sine square. Now, when this particular parabola is greater than 0, when v is less than or equal to minus 8, and v is greater than 7/8, right? Now, can sine square be less than 1/8? No, that's positive thing, or 0, but not less than minus 1/8, right? So this does not bring us any solutions. This one does. So we have to analyze basically the very simple inequality sine square greater than 7/8. That's what we have reduced our problem to. Now, how to solve this? Well, there are many ways. Obviously, you can extract square root. Actually, I prefer to do something, I think, a little smarter. Remember, cosine of 2x is equal to cosine square minus sine square, or 1 minus 2 sine square x, right? So sine square x is equal to what? 1/2 1 minus cosine of 2x. Correct? Cosine square minus sine square. Cosine is 1 minus sine, so it's 1 minus 2 sine squares. And if I resolve it for sine square, it will be here. Cosine will be there. 1 minus, yes. So, and that's invariant transformation. So I will do this. 1/2 1 minus cosine of 2x greater than 7/8. Well, that's easier because there is no square here, right? Okay, so it's 1/2 minus 1/2 cosine 2x greater than 7/8 times 8, right? So it's 8, no, that's 4. 4 minus 4 cosine of 2x greater than equal to 7. 4 cosine of 2x, it's here. It's less than or equal than minus 3. So cosine of 2x less than minus 3/4. And this we know how to solve for 2x, and then we'll just divide by 2, right? All right, so let's solve it, and that will be the end of it. Now, when is cosine of 2x is less than 3/4? Minus 3/4. So, let's say this is my cosine. 0 to 2 pi. This is pi. This is pi over 2. This is 3 pi over 2. Now, minus 3/4 is here. We need less than minus 3/4, right? So it's from this point to this point, this interval. Now, this is arc cosine of minus 3/4, right? Because arc cosine is defined on this. Its angle, cosine of which is equal to minus 3/4. Correct? Now, I can actually do it this way. So it's from arc cosine of -3/4 to this point. Now, if this is arc cosine of -3/4, sorry, this is 2 pi minus, because these are symmetrical, right? So to 2 pi minus arc cosine of -3/4. So that's the solution. And adding 2 pi to both sides will give you the complete solution. Well, that's it. Was it difficult? I don't know, it's a little tedious, I would say, because you have to really first transform your original trigonometric inequality, which contains multiple trigonometric functions, into something more bearable with one trigonometric function, but not the simple one, but something like a quadratic inequality, where the one and only one trigonometric function is the argument. So in the first problem there was a tangent, in the second problem it was sine, and in the third problem it was sine squared. And then after you solve the quadratic inequality, basically by obtaining some kind of a condition on the argument, and argument is not original x, it's like tangent x or sine square x, etc. You basically analyze the second wave of inequalities and the third if it's necessary, whatever. So by substitution you reduce the problem further and further down to the elementary basic level of style like sine of x less than whatever. So that's the methodology. Hopefully it works, and all which is required for you is to see what kind of transformation you should do with the original inequality, which is a mixture of God knows what, how to transform it into something more palatable, more understandable, which can be resolved in steps. So you reduce your complex problem to 2, 3, or 4, or whatever number more simple problems. And that's basically the approach to an entire world. Whenever you have a complex problem, reduce it to a combination of small ones, and that would definitely do the trick. Well, that's why mathematicians are the best people who can solve the problems when nobody really knows what to do, because they're trained to think outside of the box. They don't know the algorithm, they come up with algorithms, and that's what this course is supposed to teach you, I hope. All right, don't forget, unizor.com is the website which allows you to register, pass exams, enroll into different topics, basically to do this controlled educational environment. I definitely encourage you to register and to take exams, etc. So thank you very much. Try to repeat these calculations, these solutions yourself. That's very important. So you'll go again through the same problems. If you can do it by yourself, great. And good luck. Thank you. Hi, I'm Zor. Welcome to Unizor Education. I would like to continue solving trigonometric inequalities. They're not very difficult. There are 3 of them which I would like to talk about today. So, well, let's just try to do it. I'm sure you tried to solve it themselves first. Do it just by yourself, thinking about these equations, the inequalities. It's very important. So, regardless of the fact whether you have solved them correctly or not, so let's just examine what I consider might be a good solution. All right, the first one. sine of x plus cosine of x less than square root of 2. Okay. Obviously, we can do it in many different ways. I think what this particular problem actually is trying to make a point. Before solving anything like straight without any thinking, like you can just draw a graph of this function, sine of x, cosine of x, add them together, get some curve basically, and try to maybe resolve the equation when this is equal to square root of 2. Yes, you can do it this way, but obviously it would help if some very simple transformation would help you to simplify this particular inequality. So, how to simplify it? Well, in this particular case, I don't know, this square root of 2 actually kind of reminds me something. It reminds me that square root of 2 over 2 is a cosine and a sine of pi over 4. And if I will multiply by square root of 2 over 2 left and right part, it looks like I'm multiplying by sine and cosine, and that would look like a formula for a cosine of the difference between x and pi over 4, right? So I multiply left and right part by square root of 2 over 2, but since it's the same, so instead of square root of 2 over 2 with the sine of x, I will put sine of pi over 4, and instead of square root of 2 over 2 with the cosine, I will put cosine of pi over 4, and then it will be cosine of x times cosine of pi over 4 plus sine of x and sine of pi over 4, which is the formula for cosine of the difference between x and pi over 4. So, cosine of x minus pi over 4 less than 1, right? Now, cosine is always less than or equal to 1, and at what particular points the cosine is equal to 1, which we have to exclude actually from the solutions? Well, remember the cosine is abscissa, right? So, cosine is abscissa, and the cosine is equal to 0 at the angle equal to 0 plus 2pn, right? So, x minus pi over 4 should not be equal to 2 pi n, where n is any integer number, because these 2 pi n is exactly this particular angle, which means that x should not be equal to pi over 4 plus 2 pi n, where n is any integer number, and any other x but this one would satisfy the inequality. That's it. So, again, the trick is to multiply both parts by this expression. Just, think about this. If you have sine and cosine in this particular combination, it might actually be helpful to multiply it by square root of 2 over 2, which gives you a little bit simpler formula, basically. Second one. Sine of 2 pi cosine of x greater than 0. Well, this is kind of a complicated thing, so you cannot really immediately come up with the solution, even graphically, quite frankly. I never actually attempted to draw a graph of function like this one. However, we do know how to solve this particular inequality, right? So we can convert condition on a sine into condition on the y. Well, in this case, y is this. So when exactly the sign is positive, well, sign is ordinate, right? Remember. So these angles, they all have positive ordinate. So it's from 0 to pi, plus 2 pi n on both sides. So these are conditions for the angle sufficient for its sign to be positive. So this is exactly the condition which we would like to impose on whatever we have under the sign, whatever the argument to a sign is. So what I want to say is that 2 pi cosine of x should be less than 2 pi n and greater than pi plus 2 pi n. Pi plus 2 pi n. And this is 2 pi n. Right? Well, obviously we should reduce by 2 pi. It's a positive, so everything is fine. Pi over 2 plus n. Right? That's what we have. Sorry, that's 1/2. We reduced by 2 pi. We divided by 2 pi, so it's n. This is the cosine, this is 1/2, and this is n. All right, now, this is basically a condition equivalent to this one. We did not really lose anything, we did not add anything. So instead of solving the original equation, we will solve this. And by the way, this should be simultaneously, so it should be like intersection of two intervals or more intervals, whatever it is. All right, so let's wipe out this and consider this to be my problem. Now let's think about cosine is a restricted function. It's from -1 to 1. So n cannot be very big positive or very small negative value, because the cosine would be outside of this range. Now, can n be, for instance, -2? If this is -2, this is -1.5, cosine cannot be less than -1.5, right? Because of this. Now, can n be -1? It's -1, and this is -1/2. That's possible. So one of the things is where we should look for a solution is this. Can n be equal to 0? Well, yes, because it will be from 0 to 1/2, which is also good. From 0 to 1/2, it's possible. Can n be equal to 1? No, because 1 and 1.5 cosine will not be in between these two values. So basically, we have reduced our inequality original to two independent solutions. Solutions to this and solution to this. All right? Well, that's kind of easy, right? So let's just solve them. For the first one, well, let's consider the graph. That would be easier. So this is 0, this is pi over 2, this is pi, this is minus pi over 2, and this is minus pi. Now we also have -1/2 and 1/2, so this is 1 and -1, 1/2 is here. Okay, let's consider the first one. The first one is from -1 to -1/2. Now, minus 1 to minus 1/2 seems to be like this is minus 1/2. So it's this particular area and this particular area, right? So what is the value of x if cosine is equal to minus 1/2? Well, that's pi minus pi over 3, am I right? Now, cosine of pi over 3, which is 60 degrees, is equal to 1/2, right? Cosine of 60 degrees and sine of 30 degrees are 1/2. Now, when I'm changing from pi over 3 to pi minus pi over 3, now obviously, if this is pi over 3, this is pi minus pi over 3, and abscissa would be the same by absolute value but negative. So we need minus 1/2. So that would be minus 1/2. So this particular point is pi minus pi over 3, which is 2 pi over 3. Now this point correspondingly is minus 2 pi over 3 because cosine is an even function. And these are obviously minus pi and minus pi. So the solution to the first one is to make cosine from minus 1 to minus 1/2, we have to make x from minus pi to minus 2 pi over 3. Am I right? Looks like I'm right. And from 2 pi over 3 to pi. This is this area. And obviously I should add 2 pi n to both sides. So these intervals are solutions to the first one. Okay, now solutions to the second one, from 0 to 1/2. So from 0 to 1/2, so it's this. From 0 to 1/2, it's this piece and this piece. The cosine would be from 0 greater than 0 but less than 1/2, right? So what are these intervals? Well, 0 is obviously minus pi over 2 and minus over 2, and 1/2 would be pi over 3 and minus pi over 3, right? Because the cosine of pi over 3 is 1/2. So in this particular case, we have from minus pi over 2 to pi to minus pi over 3, from minus pi over 2 to minus pi over 3, and from pi over 3 to pi over 2. That's this piece. And again, I should use 2 pi n in both cases. So, these are 4 different groups of intervals. Now, why groups? Because of this n. N is any integer number. So for any specific n, we have 4 intervals, which is this one, this one, this one, and this one, where this particular condition is, where original inequality holds true, right? Okay, that's it. So what did we do here? Let me just summarize it. We reduced the original quite complicated inequality into a combination of simple ones. So from sine of something, sine of 2 pi cosine x, we have reduced to condition on 2 pi cosine x, and from that we have reduced it to condition on x. So it's like 2 steps procedure. And the third problem which I have is cosine of pi xy greater than 0. Okay, now the first question you might ask is, hey, we have only one inequality and 2 different variables. Well, that's right, which means that solutions are not expressed in some kind of a inequality for x, but it should be an inequality on x and y. And how can we express it? I mean, graphically, in the previous cases, we always had some kind of interval, x from this to this, or from that to that. That's one-dimensional intervals on the line. Well, this obviously is a 2-dimensional area on the plane, on the coordinate plane. Question is, how does it look? So my purpose right now is basically express it not only analytically, and analytically to express it, it's very easy. The cosine is positive, as you understand from, here is the graph. So this is 1, this is minus pi over 2, and this is pi over 2. Right? So cosine goes like this. So it's positive between minus pi over 2 and pi over 2, and plus 2 pi n, obviously, right? So I can very easily express the condition on x and y by basically saying that pi xy should be from pi over 2 plus 2 pi n to minus pi over 2 plus 2 pi n, right? But what is this? I mean, in case of intervals, you just see, okay, any x which belongs to this interval is a solution. Now, which pairs of x and y belong to this particular solution? Well, for instance, x and y equal to 0 does fit, okay, but what else? So we better express it graphically. So my point is right now, you cannot really express it analytically better than this one. I mean, obviously you can just resolve it for y or for x or whatever. But it does not really give you the feeling of what exactly the solution is. That's why I would like to approach it graphically. All right? So, how can we approach it graphically? I suggest we slightly change this. Well, first of all, we obviously can reduce it by pi. So I will have xy between minus 1/2 and 1/2. Xy between 1/2 plus n and minus 1/2 plus, no, 2n, sorry, 2n. Now, for every n, we have its own area of x and y, you see? Let's say for n is equal to 0, we have xy from minus 1/2 to 1/2. Now, what is it? Well, let's just think about it. Let's put n is equal to 0 first. Now, our xy is from minus 1/2 to 1/2. Now, how does it look graphically? Well, let's think about it. Let's build the first one. Xy less than 1/2. Well, let's build let's build xy equals to 1/2. That probably divides the whole plane into two parts, where it's less than 1/2 and where it's equal to 1/2, and the division point is where it's equal to 1, where it's equal, right? So this is hyperbola, right? Because for positive x we can say y is equal to 1/2 of 1x, right? Now y is equal to 1x is just a hyperbola. 1/2 it's just slightly squeezed down by now, and on the negative side it's this, right? So these are two pieces of the curve which supposed to divide the whole area into the whole plane into areas where xy greater than 1/2 and less than 1/2. So in this particular area, let's say take 0, 0. 0, 0 is obviously less than 1/2. So the whole area which is in between these two is less than 1/2. Here xy would be greater than 1/2, and here it would be also greater than 1/2. So that's how we have divided our plane into different areas, right? Now, what about xy greater than -1/2? Well, again, first of all, let's draw y is equal to -1/2 of 1x. Now that would be this, right? These two curves represent this particular graph. And now we need, again, how does it divide the area? Well, same thing, 0.00 is greater. So in this particular case, again, 0.00, which is in between these two, belongs to the area where xy is greater than -1/2. And whatever is outside, this is xy would be less than -1/2. This would be xy will be less than -1/2. So what I want to say is that this particular combination of these two inequalities is this diamond kind of shape. Well, I mean, it's obviously not a diamond because it's infinite in both cases. In all four sides, actually, it's infinite. It's asymptotically approaching the axis, but it still looks like a diamond, basically, right? So that's what it is. This is this particular area which is represented by this particular two inequalities, when xy is greater than -1/2 and less than 1/2. It's this area in between these four lines. Okay, fine. That's done for n is equal to 0. Let's move on. Okay, so far we have this particular piece of the plane as a solution to our initial inequality. Now, let's move on with n. Let's say n is equal to 1, all right? So when n is equal to 1, I have here 2 minus, so it's 1.5. So 1 and 1/2 xy less than xy less than 2 and 1/2, right? What is this? Well, again, let's build two curves. First, xy is equal to 1.5, and then we will take whatever is greater. Now, what's the difference between this, which is actually y is equal to 1.5 times 1x? What's different from this? This, if you remember, was 1/2 times x, times 1 over x. And this is 1.5. So it's higher, basically. So if original was a standard hyperbola, y is equal to 1 over x squeezed down by the factor of 2, then this one would be stretched up by a factor of 1.5. So it would be higher. It's always higher than this one. And what we are looking for is values which are greater than this one, which is this one. Now, similarly, with the negative x, it would be this, and the area would be this. Now, how about 2.5? It should be less than 2.5. So that would be, the coefficient would be 2.5 and would be parabola even, hyperbola even higher than that. But now the condition is less than. So combination of these two would be area in between these two hyperbolas. So this is not a solution. So in addition to this diamond kind of thing, we have a stripe from 1.5xy to 2.5xy. Now, obviously, if we increase n, we will have, for n is equal to 2, we will have what? 3.5 and 4.5, right? So it will be even higher. So again, two stripes will be added. It will be here and here, etc. So I will add stripes. Now, with a negative n, I will have, let's say, -1. If it's -1, so it would be what? Minus 2.5, and this is -1.5. Well, obviously, it would be stripes on this side. So in addition to this diamond kind of area, which is the result of this thing with n is equal to 0, I will have additional stripes. These stripes would be added as n is equal to 1, 2, 3, 4, etc. positive, and these stripes would be added as n is equal to -1, -2, -2. So the combination of all of them is this type of geometrical area, diamond-like in the middle, and then stripes around it. But all of these stripes are asymptotically tend to axis, so they are narrower and narrower as we go either to the right or to the bottom or to the left or to the up, right? So that's basically how this area, which represents the solution to the original inequality, looks like. Well, it might be a little, complicated. I don't know, but I think this graphical representation really helps you to better feel what exactly all these inequalities are. And don't get scared by the fact that you have two variables and only one inequality. It just means that the result would be a two-dimensional area on the plane rather than one-dimensional interval or a set of intervals on the line. Well, that's it. I do recommend you to go through these problems again, just by yourself. And don't forget that everything is on unizor.com, where the whole educational process actually can be utilized by you. And it has exams for registered students. Your supervisors or your parents can enroll you into different topics, can consider and mark these topics as completed if the exams which you did, which you took, are passed to their satisfaction, etc. So again, try to do it yourself as much as possible, all these problems, before you listen to lectures like this. And that's it for today. Thank you very much and good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to continue talking about trigonometric inequalities, but in this case, instead of solving the inequalities, which means given an inequality, find arguments when this particular inequality holds. It's slightly different twist in this particular topic. You have to prove that certain inequality is held if certain restriction on arguments is given. Well, there are certain unconditional inequalities. For instance, in trigonometry, you can always have that sine of x is less than or equal to 1, right? But something like this, just equal without the equal sign, just less without the equal sign, if x is not equal to pi over 2 plus 2 pi n. Now this is a conditional inequality, so if this condition for an argument is established, then you have this particular inequality held true. So a few examples of this particular thing I'm going to present right now. And the first one is related to an interesting observation which you might or might not actually made before. If you consider the graph of the function sine, something like this. Well, obviously it goes here as well. It might actually come to your eyes the resemblance of this particular direction of the function y is equal to sine x, and a straight line which basically represents y is equal to x graph. And this is y is equal to sine of x. Well, so the question is, on this microscopic level, whenever you are very, very close to the point 0, how actually this angle bisector, which is y is equal to x, and sine, how close they are. And here is a very interesting theorem. I'm not going to prove this particular theorem right now, that's for the later, but basically the point is that they are so close that the ratio between sine x and x, this is sine x and this is x, right? Sine x, x. So this ratio actually goes to 1 the closer we get to the 0, which means they are very, very much close to itself. However, this particular line, y is equal to x, is always above the sine. So sine goes underneath, but very close. So close that the tangential line to a graph of the sine actually is y is equal to x. It's like you have a circle and the horizontal line, which is a tangential line to a circle, very close to the circle in this particular case. They are basically almost the same. So this is tangential to a circle, and this is tangential to a sine in this particular point. So from these qualitative observations, I would like to go to a more analytical one, and basically, as the first step in investigating the behavior of these two things, I would like to prove that sine is always less than x if x is in this particular interval from 0 to pi over 2. So I'm considering the sine only in this particular area from 0 to pi over 2. And in this area, sine is always below the line y is equal to x. That's what I'm going to prove to you. Okay, so that's what I want to do, but I don't want to do it on this graph. I will use some kind of a geometry in this particular case, and you know, sometimes it's considered to be like a bad taste if you depend on the drawing very much when you're proving certain theorems. However, you can always make it a little bit more rigid and strict and robust, etc. That's not my purpose. My purpose is just to explain the reason why this particular inequality actually is held. So let me consider a unit circle. Doesn't look like a unit circle. Oh, this is a nice unit circle. And now I'm considering angles only from 0 to pi over 2. So angles from this position to this position, greater than 0 and less than pi over 2. So this is an angle. And for any angle in this category, I would like to prove this. Okay, here's how I'm going to do it. Let me draw a chord AB. Let's say the angle is x. And I'm talking about radians, obviously. I mean, if you will change it to degrees, it will definitely be wrong. So, I mean, all right. So, we are talking about radians, and that's the case in this particular case. Now, I consider the altitude of the triangle OAB, AC. Now, this altitude is actually an ordinate of the point A, right? This is ordinate and this is abscissa. So, ordinate of a point on a unit circle is equal to sine of the corresponding angle. So AC is sine of x, where x is an angle in radians. Now OB is equal to 1 because it's the unit circle. So the area of the triangle OAB is equal to the base, which is OB, which is 1, times the altitude, which is AC, which is sine of x, and 1/2 of this, right? So that's the area of triangle OAB. Now, how about the area of a sector OAB? Sector is piece of the, like a pizza pie, basically. So it's a slice of pizza. All right. Now, number one, obviously it's bigger than the area of a triangle by this little piece, right? Chord is always inside the circle, so the area of the sector is definitely greater than the area of a triangle OAB. Now, what is the area of this circle? Well, we know that the area of this sector is proportional to the angle, right? So the total angle in radians is equal to 2 pi, and the total area of the circle is equal to pi r squared, right? Now r is equal to 1, so it's pi. So this is the total angle, this is the total area. Now, our angle is x. So what is, now proportionality should be preserved, right? So what is supposed to be here? Well, obviously x over 2, right? So this is angle and this is angle. Our angle and the full angle. Now this is area and this is area. Area of a sector and area of an entire circle, right? So this is equal to x over 2. And since area of the triangle is less than the area of a sector, I can conclude from this that 1/2 sine of x is less than x over 2, which means that the sine of x is less than x, which is to be proved, right? Now, that's it. That's the first trigonometric inequality I wanted to present to you. And again, don't forget that I'm talking right now only about angles x from 0 to pi over 2. I'm talking about acute angles only. Well, that's the number one. The second inequality which I would like to talk about is about tangent. And I would like to prove that tangent x is greater than x. Again, if x belongs to interval from 0 to pi over 2. Okay, how to prove that? Well, I'll use basically the same approach. What I will do in this case, just like this out, I will continue this line, and this is the perpendicular. So this is A, B, C, D. Okay? Now, the triangle ODB is greater than the sector OAB, right? The area of a sector, so area of a sector OAB, we have just concluded this is x over 2. Now, what is the area of ODB? Area of triangle ODB is equal to base, which is OB, which is 1, times altitude, right? Now, what is altitude? Think about tangent. Tangent is, in any right triangle, is a ratio between the opposite catetus to the adjacent catetus. So tangent of x is equal to dB divided by OB. OB is 1. So dB is a tangent. And we have to divide it by 2, right? Base times tangent of x and divided by 2. And now, from the same geometric consideration, since the area of a triangle ODB is greater than the area of a sector, we have come up with tangent of x over 2 is greater than x over 2, which means tangent of x is greater than x. So x is in between sine and tangent of x. Now, let me go back to the graphics. It's very interesting to see graphically. What I'm talking about is the following. If this is y is equal to x, then this is y is equal to sine of x, and this is y is equal to tangent of x. That's how they behave locally, very close to 0. They are coming into the same thing, but sine from the bottom and a tangent from the top, and they are all kind of straightening their graphs So at 0 they are basically parallel to each other. That's what's happening. That's the behavior of these functions. Now, from this particular point, which we have just established, this one, we can very easily derive a couple of other things. For instance, since x is less than tangent of x, now you know, now they're all positive. We are talking about x always from 0 to pi over 2. So we know that if we invert numbers, then the relationship between them is also inverted, right? So if x becomes a denominator and tangent becomes denominator. So since this denominator is greater than this, then the fraction correspondingly would be smaller, right? Now what is 1 over tangent? Well, it's cotangent of x, right? Remember? This is cosine of x divided by sine of x. That's the definition. Tangent is sine of x over cosine of x. Now, what else can be said around here? Well, from this, you can always multiply it by sine, and you will have that sine of x divided by x is greater than the cosine. Right? So cosine is smaller, so I put it on the left. Now at the same time, since sine of x less than x, let's divide it by x, and we will have x is positive, so nothing actually is changing as far as the inequality is concerned. So sine of x over x is less than 1, right? If I divide it by x. So I have this. And here is what's interesting thing. As x is getting smaller and smaller, the angle, so in the graph, we are getting closer and closer to 0. So sine x divided by x, now this thing, if x goes to 0, cosine of 0 is 1, right? So it goes to 1 basically. Now this one also is not changing, that's 1. So sine of x divided by x on both sides, smaller and greater, have boundaries which are gradually going to 1. Now what does it mean? What's the behavior of sine of x over x? It's also supposed to go to 1. So, and that's exactly what I meant, that around 0 sine of x is straightening, and it's almost the same as y is equal to x. But I'm not proving this right now. This is just an explanation so you have a feeling of how sine over x behaves around the x. And same thing with tangent as well. But it's just straightening from the top. Sine is straightening from the bottom, and tangent is straightening from the top. But around 0, they are all very, very, very close to y is equal to x. Okay. That's it for sine and cosine. Now let's move on. Okay, what else is interesting? Sine of x times cosine of x is less than or equal to 1/2. How can we prove this? Basically for any x. There are no restrictions here, it's unconditional. Well, I'm sure we remember the formula for sine of 2x, which is 2 sine x cosine x. Right? So, obviously, sine of 2x is less than or equal to 1, because sine of anything is less than or equal to 1. And since sine of